pleasure to welcome the first speaker, Eric Xing from Carnegie Mellon, and he's going to talk about sparse learning.
Okay, I'd like to begin by thanking the organizers for inviting me here. I heard a lot of exciting talks this morning. I hope I don't disappoint you with a not so exciting talk here. Sorry. I shouldn't probably step away from the microphone or, oh, I didn't wear this. I see.
I actually failed it. So clearly I failed in my duty as a session organizer here. And you should put that close to your mouth, like here. Fantastic.
It is on already?
Should be green.
Yeah, it's not green yet.
Why isn't it green? No, it's off.
Okay.
Try it.
Yep. Okay, so can everybody hear me now? Great. All right, so I'm Eric Xing, and I just said I appreciate the organizers for inviting me here. So what I'm going to talk about. So recently, as a result of my spending my sabbatical time at Facebook, I got very excited about very large-scale applied problems. And so I'm going to share with you some of the progress we made along this direction in terms of coming up with right models to solve large-scale problems, and also many of the computing issues are involved in solving those models efficiently. So what are the nature of these large-scale problems? Here I give you a few examples. So the problems nowadays we might be interested in are really huge in terms of the kind of data they handle and the kind of complexity they have to deal with within the data. For example, in this genomics problem, usually your data is the entire genome of a human, which can contain several billion characters, some of which, like millions of which, are mutations, which could be treated as covariates. And then the response variable could be also in very high-dimensional space, such as the response in a couple of thousand genes, which are connected by also a network. Similarly, in problems that is closer to computer science, such as a computer vision problem, usually nowadays in companies like Facebook and Google, we deal with a data set of this big, like a couple of billion images. And then you want to put a label, for example, of those images. And this labeling space is also very big. It's not like you label 1 out of 10 different objects. Instead, you are labeling in one out of a few tens of thousands of possible outcomes. And those outcomes can be also organized in a complex taxonomy. Just to be more specific, in one of the problems I work on, known as the genome association problem, you want to build a causal structure from the input genome to the output gene expression pattern. And in many of these problems, our data are in a very high-dimensional space, but the amount of data available for doing this inference is very small. Therefore, we are running into this very severe, n smaller than p problem, which, demands you to do appropriate regularization. And in particular, in many of these problems, we actually know a lot of knowledge about the structure of the data, such as certain genes being connected into a graph, certain sites on the DNA being coupled genetically or just physically during their inheritance. So now the question is, if you know all this structure, can you use all of them to simplify the inference of the structure problem that I just mentioned? Similarly, in computer vision, the problem I'm dealing with is of this nature. I'm giving you, I'm given a few million images, and then I need to find the right label of this image. And these labels are usually very structured, to the point that they can be organized into a big, ontology, which can be borrowed from the very well-known WordNet from Princeton, which means that every concept is an entity organized in a tree type of structure. But this data structure is also very big. They are big in very different dimensions. First of all, the data volume is very big, the dimension is very high, and also the number of classes to be predicted is also very many. So at the end of the day, we are landing at this type of domain where the problem is big in all three senses, meaning that they are big in volume, they are very large in dimension, and they are also very large in concept space. So how can we deal with problem of this nature? So it is recognized by many practitioners that here might be the way to go. First of all, whatever inference algorithm or computational procedure you have to run, they probably have to treat with data points one by one in a stochastic or online fashion rather than take the entire data set in a single computational step, such as a gigantic gradient. And secondly, because of the high dimensionality of the data, you now need to do some kind of reduction either for computational purpose or for interpretational purpose. Therefore, you need sparsity, you need some type of sparse coding technique, and also you may need to encode structures in those kind of sparsification. And similarly, on the output side, because your concepts or your predictors are so many and also highly correlated, you may also want to solve multiple problems together in the so-called multitask learning or transfer learning scenario, where structure sparsity should also play a role. So that's the kind of domain that I want to talk about, and also to propose a few models and also a generic computational algorithm, hopefully to solve the models in a fast fashion. So here comes the outline of my talk. So to begin with, let's start with a very simple model where everything began. We all know that in the linear model, in order to impose some kind of sparsification preference or bias, you want to introduce a L1 norm, which is going to play the role of shrinking certain covariates into zero weights. But it is well known that this kind of shrinkage function is not taking into consideration of any structural knowledge. Therefore, if you know certain variables are coupled in a certain way, you cannot make explicit use of that. Therefore, later on, people invented a number of fancier structure regularizer, sometimes capturing group structure and sometimes capturing graph structure. So in the spirit of the problems I talk about, let me give you a few examples of this kind of structure. For example, when we want to do prediction of a multiple outcome, it is well known that when the multiple outcomes are coupled in such a fashion, for example, it is not ideal to predict every label separately, say predict whether the color is red or not red, green or not green. Rather, you want to make a structured prediction to make the output to be dependent of each other. So in this structured prediction setting, you need to use a model that is slightly more complicated than the linear regression model I just indicated. For example, in this case, you have a multiple output, say 5 outcome, which correspond to the label of this image in a 5-dimensional space. But on the other hand, the label can be also coupled because 3 of these labels belong to a class called dog. The other 2 correspond to the class of birds. And if you know this structure, do you want to solve the classification problem of this input image separately or jointly? We want to argue that it is probably better to solve them jointly, in the sense that we want to learn a predictive structure which is of this type of pattern. For example, for those predictive functions which are commonly pointing to the output of a dog label, then their weights should have some shared pattern, maybe some different pattern, but also they should have something to be shared. On the other hand, there may be also structured input space where you may believe that in the image, the upper part corresponds to sky, and the lower part corresponds to land, and the middle part corresponds to objects. Then it makes sense also to group features into a non-random fashion so that they can be penalized in a joint fashion. Therefore, there should be also coupling along this dimension. So in a way, we want to introduce some technique to regularize either column or rows of the coefficient matrix so that when they are estimated and shrinked, they should be shrinked in a coupled fashion rather than independently. So that requires us to design some interesting structure regularizer called which we call structure sparsity induced norm. In this case, I'm going to introduce 2 of them, which are known as graph or tree-guided penalties. For example, suppose that we know that given this feature vector of input data, our predictive concepts are living in a high-dimensional space in which each concept can be coupled with some other concepts. Say this is a particular kind of dog, that is another kind of dog, but on the other hand, the label of chair lives in here. Therefore, it makes sense for these 2 labels to be more closely related. So if we know this kind of output structure, what should we do? One argue that maybe we want to introduce some dependencies of the label or of the coefficients from this feature to that label and to this label in the sense that their differences should be penalized. So this is a kind of a simple graph-guided fusion function that can be used to regularize the model inference. Similarly, if you know that the concepts are organized as a tree, you can also introduce some elaborated tree type of penalty, which is going to impose two separate pooling force. One is to penalize each coefficient vector separately, and the other is to penalize each coefficient all the coefficient vector jointly because they are under the same branch under a particular tree. And in the extreme case, this penalty function is similar to an elastic net, but when you have a general tree, the function can be pretty complex to have this nested summation structure. So all these different structural regularizers now has been proven to be very useful in deriving interesting and useful models. And here I want to just skip over more utility of this particular technique in different settings and go to the mathematical challenge we have. So it is a challenging problem because the introduction of this structure sparsity inducing penalty is going to cause the computational inference problem very hard for many reasons. For example, suppose this omega function is now designed to be capturing overlapping group structure or maybe tree-guided fusion structure. Then it turns out that this omega function is no longer separable according to beta. Therefore, you cannot simply derive simple gradient on top of that. And also, this penalty function is no longer smooth. Therefore, at some of the corner, you cannot even compute a gradient value very specifically. So that renders many of the existing optimization algorithms cease to work properly in this very complex setting. For example, here I have a few examples. The classical and the generic solver for a convex program is known as interior point methods. They are a class of fairly sophisticated method which can be applied to a wide range of complex structure-inducing norm. But on the other hand, their efficiency is very low because they need to solve at every iteration step either a Newton system or some other complex computation which can take a lot of time. Therefore, they cannot be scaled to any problem with dimension more than a few hundreds. Some recent techniques, such as subgradient methods or block coordinate descent algorithms, are making use of some special structure in the penalizer, in the penalty function, to derive very specific tricks or techniques to speed up the computation. But on the other hand, either their speed is still not quite high enough, or they are limited to a particular type of structure. In our case, for example, the two structures I just introduced, which includes the overlapping graph structure and also the the graph-guided fusion structure, these algorithms cannot be easily applied. So my goal here is to introduce a very simple but very effective technique so that you can come up with an efficient optimization algorithm for a general class of structure sparse-inducing norm, as I described. And this technique is called smoothing proximal gradient descent algorithm with the following spirit. First of all, we recognize that it is always good to avoid computing, avoiding any second-order technique or any, specific, blockage or projection method because they all involve complex computation. We want to use simple gradient methods because they are scalable and fast. But on the other hand, in order to make this gradient method useful, your loss function or your objective has to be separable and have nice properties, which is not, the case in the problem I just described. So our problem is how to re-engineer our problem to make them feasible to apply a gradient-based method. And here's the idea. First of all, we want to reformulate our structured sparsity-inducing penalty into a nicer form so that they become separable. And then we're going to introduce some smoothing term so that this reformulation also becomes smooth. And then you have a separable and smooth function where you can now start to apply the very efficient gradient-based technique to do fast gradient descent in order to solve the problem. For example, let me give you the specific incarnation of this technique in the models I just described. Let's say how to reformulate this fusion function. So this is the generic form of a fusion function where the two coefficients needs to be subtracted from each other so that they can generate a total variation difference penalty. And here we first use the technique, introduce a incident matrix to indicate where such subtraction take place. And then we want to use a technique known as a dual norm to rewrite this, this L1 penalty into the solution of a optimization problem like this, okay? So that we can rewrite the original norm function into this form, which makes the beta coefficients all separable. Okay, so this is a algebraic game that you can always play to design the right C so that we establish equivalence of this form to that form. And the similar technique can be also used for reformulating the group penalty, which I don't want to go into detail because they are kind of tedious. You can look at a paper we're going to publish very soon to see how this can be generally performed. So at the end of the day, we are going to rewrite our loss function into a dual norm form like this, which is nice looking because they become separable in terms of beta. But nonetheless, they are still not smooth so that you can perform a gradient or differentiation over beta. What we do next is to introduce a smoothing function called the d alpha, which is to bump up at certain corners where the function over beta is non-smooth to be smooth. Okay, I'm going to show you actually a geometric picture in the next slides to give you intuition why that can happen. And by combining this smooth function with the original dual norm, now you have a new function f mu, which is parameterized by mu, and it defines a lower bound of our original loss function, our original target function. And this lower bound actually can be controlled by setting the value of the mu to be correct, to be appropriate. In fact, in our iterative algorithm, we're going to sequentially, iteratively tighten this gap so that we can approximate the true function closer and closer in a very fast fashion. So here is the geometric interpretation. You have original loss function, penalty function, which is non-smooth along the dimension of the parameter to be optimized. But by introducing this adapter, which is an auxiliary function, on top of the original one, you suddenly can see that this corner where things become non-smooth gets smoothed out, so that you can apply any differentiation function on top of that. So that brings us to here. We are having an original problem which has a loss function of a very generic form as long as it's smooth and convex. You can use a likelihood-based loss or a square root residual penalty and stuff like that. And then here you have the structured sparsity inducing norm, and plus also a non-smooth but simple L1 norm to make sure that every coefficient are still going to be sparse if there's no other constraint. And then we are going to approximate this whole thing by replacing the sparsity, the structured sparsity inducing norm with this surrogate function, which is separable and smooth. And then we are going to compute a gradient over this entire loss function. We can prove that this is Lipschitz continuous, therefore it has a nice behavior in terms of driving down to the convergence. Okay, so that brings us to the algorithm. Because now we are in the space of a smooth penalty function, and with a very benign and nicely separable non-smooth term of L1 norm, we can basically use existing technique, such as the one developed by Beck and Trebolet, which is called the FIST algorithm, the fast shrinkage thresholding technique to do a gradient-based approximation. And here is the formula. The key in here is that you want to solve this function in every update step, but because of our reformulation of the structured sparse inducing norm, now this function is solvable in closed form. Therefore, you can rapidly do update at every step until you get convergence. We can show that this particular procedure are converging at a very nice rate. In fact, it is converging at a rate of 1 over epsilon. Epsilon, by the way, is the error. It's the gap between our approximation and the true loss function. To contrast, the well-known subgradient method that is often used for this type of problem has a convergence rate of 1 over epsilon squared. There exists some specialized technique which has a convergence rate of 1 over square root of epsilon, but we found that these kind of techniques are very specialized and rely very heavily on the structure of the penalizer, which is not actually easily derivable for the type of problem I just described. I'm going to skip the proof idea and move down to time complexity. So what I showed just now as the convergence rate is the number of steps to converging. But people also want to ask, what is the per iteration cost? It turns out that the per iteration cost is not too bad. It's actually comparable to many of the existing techniques or even better. For example, here, suppose that we can pre-compute this matrix, the design matrix, and we can also at every iteration, what we need to do is basically to compute this value. You can see that this value is not dependent on n, which is the number of data points in our data set. Therefore, the per iteration complexity is independent of the sample size. This is a nice property which contrasts the previous method in the interior point methods, where they need to solve a Newton system, which inherently needs to bring in the complexity of the data so that you are paying a much bigger cost. So this is the complexity for the SPG, the smoothing proximal gradient method applied to a univariate regression with structures on the input. Similarly, we can extend the technique to a multitask regression by just slightly re-engineering, the way we want to, design this incident matrix to encode the structure penalty live on the output space. So all the technique I just introduced will apply to here, which leads to a similar contrast of complexity improvement and convergence rate. And just to give you a big idea, here is the complexity of per iteration that you need to pay for a IPM-based technique, and which you can see has a very dramatic turn here that depends on the sample size, and also a quadratic term which is quadratic over both the input dimension and also the output dimension. In our case, we don't have a dependency on the sample size per iteration, and also we don't have this quadratic term over the input dimension, over the output dimension. The output is linear, only the input is quadratically dependent. Therefore, this algorithm scales much better than the previous method available. To show you the performance of this technique, we did a number of experiments, both in simulation and in real data. And this graph basically shows you that it is a good idea to use this kind of structured sparse inducing norm to do structured inference. You can see the advantage of the inference from our model compared to other models, which is not introducing structure. So this is the true coefficient structure we want to estimate. This is our estimated one, and these are the ones estimated by other models. You can see a lot of noises in the estimator, and here we have a clean pattern. But what I really want to show is this graph, which is the comparison of the time complexity. You can see that this is a log scale plot on the time complexity, and our model scale pretty nicely, in all different dimensions, where your number of output grows, your number of input grows, and your number of samples grow, and we can all scale pretty gracefully into a manageable time complexity. Whereas the other technique based on the second order comb programming is scaling, is order of magnitude slower than our technique. This is for the overlapping group lasso, and similarly, you see the contrast of time complexity, maybe even more dramatically over the graph-guided fuse lasso, where both the second order comb programming and the quadratic programming are doing really bad, when they run into high-dimensional problem, and our technique is gracefully growing up in terms of time complexity. We applied this technique to a number of applied problems. One of the favorite is the ImageNet computer vision problem I just mentioned, where we have a gigantic training data set and also a very rich input space which contain somewhere like 20,000 features and also 1,000 different concepts. This is a subset of the entire ImageNet problem for image classification. And we found that we are achieving a pretty significant performance gain over traditional models that is not using structure. People know they want to use structure, but because of the computational issue, they could not really implement such a model. So with the help of the algorithm I just described, we were able to make that happen. And then we see this performance gain. So according to, for example, a hierarchical scoring function, we can see that our model improved over the previous one by a couple percentage point. And here are just some examples showcasing the interesting mistakes made by a competing model and our and corrected by our model. For example, here I think the competing model was considered this as a geyser, and we correctly labeled this as a volcano, stuff like that. So I think I'm done with my talk. To summarize, I showed you the need for using a structured sparse inducing norm in various applied high-dimensional inference problem. And I talked about a very generic approximate optimization algorithm known as SPG, which is focusing on three techniques. First, reformulating the not so nice behaving penalty function into a nice behaving one, and then approximate with a smooth approximation, and then based on the smoothness and the separability, we can apply simple algorithms existing in the literature to speed up the inference. I think I'm done with the presentation. Thank you very much. Sure.
So in your count on the number of iterations, you say you gain a factor 1 over square root of epsilon, but you lose a factor square root of d.
I lose, where do I see?
Actually, you should repeat the question.
Okay, so that gentleman was asking, when I show the convergence rate, I'm gaining by the convergence rate was 1 over epsilon in terms compared to 1 over epsilon square of the competing algorithm, but I have a factor of d in the denominator. That's what you meant. Yeah. That's yeah. Well, that d value is a fixed constant that is dependent on data, and we can pre-compute it. And and also there are ways of approximating. Actually, for those epsilon square convergence rate, they also have some constant there, which I didn't show. So from an empirical experiment, we found that we do actually outperform the competing algorithm in terms of speed by a pretty significant margin. But again, I acknowledge the d could be something that can drive up the cost in certain cases. Yeah.
There was last year, Julian Francis Bach had a very nice scientific paper on three structures, partially, and they had a very efficient, what it looks at least to the reader, a very efficient sparse coding technique. Can you comment on?
Yeah. So the question from that gentleman was, there was a paper from Francis Bach last year in ICML where they developed a tree group regularization technique along with a inference algorithm that seems to be very fast. Yes, we're aware about that technique. In fact, in our paper, we compared all the known approximate optimization technique nowadays available for this different structured sparse penalizer. So the comment is the following. Yes, that algorithm was very fast. It is as fast as our one because we did a formal comparison of the time complexity from a notational point of view, a symbolic point of view. But we found that that technique is not generalizable for other structures. So the point here is that this single technique can be applied to most of the structures we know exist in the literature without additional work. And we found that to be appealing. Okay, thank you. Yeah.
How does your algorithm compare to coordinate descent algorithm or block coordinate descent algorithm?
Okay, good question. So he was asking how this algorithm compared to a coordinate descent with a block projection. Yeah, for overlapping group lasso or other complex structure, you cannot derive such an algorithm because the projection can be not made possible due to the overlapping between groups. Yeah, you can use it for group lasso, and in that case,
Block coordinate descent is for group lasso.
yes.
Also for fused lasso.
Mm-hmm.
I think there is a paper from the Stanford University.
Yeah. Yeah, I know that. Sure. So.
It's a report, it's not a paper.
Yeah. So thanks for bringing this up. Yeah, this is a paper from Tipshani's group on block coordinate descent. As I said, they really depend a lot on the structure of the constraint. One particular notion is that the group structure has to be non-overlapping so that they can compute the projection. In our case, if you have a generic overlapping group structure, such computation cannot be conducted in closed form. Therefore, it becomes very complicated.
So in your paper, you compared those techniques?
It's hard to compare because his algorithm cannot be implementable in this particular model because we are using an overlapping group, which is more constrained. Thank you very much.